So we're going to be looking at chapter 4. Chapter 4 is called Roots of Polynomials. And it says at the top that this chapter is about the underlying relationship between the coefficients of a polynomial, so those are the a, b, and c in ax squared plus bx plus c, and the roots of the polynomial, i.e. the values of x which make the polynomial 0. So this is linking back to some of the things you've done in pure maths, but really what we're looking here is just at patterns and relationships. There's not an awful lot of real life applications of roots of polynomials, but what is interesting about this is just that these connections exist, and we like to explore these connections that exist. So we're going to be looking about quadratics, cubics, and quartics. We're going to be thinking about the relationships between the coefficients and the roots. We're then going to be finding the values of expressions based on the roots of polynomials. So we're going to think about finding the sums of the squares of the roots, and you do all of this without even solving the equation. So we never really solve equations here, we're more just thinking about patterns. And then the last thing that we do is when we transform some of the roots, what the polynomial might change to as well. All of these things will make a lot more sense when we dive in and have a look at them. So as a bit of an introduction here, I have got a quadratic plotted on this graph, and clearly the roots of this quadratic are at -2 and 5 where it crosses, and the quadratic is x squared minus 3x minus 10. And what the purpose of this chapter is to try and do is to understand the underlying relationship between the roots of the polynomial and the coefficients of each term that we've got here. And we actually know some of these things already. So what do you notice about the sum of the roots? Well, the sum of these roots is -2 plus 5, which is 3. And this happens to be the negation of the coefficient of the x term. We knew that already because of how we know how to factorize things like that. And the product of the roots, the 5 and the -2, is -10, and it happens to be the constant term in the polynomial. So this is kind of like the general idea, but we're going to stretch it way further to be able to look at cubics and quartics and spotting more patterns that we aren't aware of. And I've said here this isn't exactly surprising because at GCSE you found the factorization of a quadratic by finding two numbers that added to give the middle number and multiplied to give the last number. And this in turn allowed you to find the roots, okay? So obviously this one, the sum of it is negated because when you factorize it, you negate whatever the value is that it's factorized with, okay? So this is the general idea of what we do here. So we're going to more formally determine what the relationship is between the coefficients of the polynomial and the roots. And just as a bit of a side note here, be really careful that when you write the letter A, I know you know how to write the letter A, obviously A looks like this, and alpha should look different to A. They are not the same thing. One is the Latin letter A, and the other one is the Greek letter A. This is the Greek letter A that we've got, which is alpha. You're also going to have to use this letter, which is beta, so you start from the bottom, and you kind of go around like that and draw a capital B. Does anyone know what comes after beta? Gamma. Yes, so it goes alpha, beta. Gamma looks like a kind of loop, like this.
It looks like a Y.
Yeah, it looks like a Y, but I also think of it kind of looking like a loop as well. And do you know what comes after gamma? Delta. And delta, you start at the top and you do this kind of squiggle, and it looks like the letter D, but like a fancier kind of one. The reason I've written these four roots here is because across this topic, we're going to start off with quadratics, cubics, quartics. So we're going to need to use all four letters when we get to quartics. So just be aware we're going to be using these. Okay, so in this bit that I've got on the left-hand side here, it says if alpha and beta are the roots of a quadratic, ax squared plus bx plus c, then clearly ax squared plus bx plus c could be written in this form that we've got here, because this would mean that alpha and beta were roots. But I've also put the a outside the front because it doesn't matter about what that a is if I have something outside the front. The roots are still going to be alpha and beta. So what I'm going to do is expand all of this right-hand side, and then I'm going to compare the coefficients that I have on the right-hand side to the coefficients that I have on the left-hand side, and hopefully I'll be able to spot what the relationship is between A, B, and C, and alpha and beta. So it's an identity, which is why I've got these three lines here. When I expand these brackets, I will have x squared as the first bit. At the end, I will have plus alpha, beta. And then in the middle, I'm going to have minus alpha x minus beta x. But I'm going to write that as minus alpha plus beta x. Because that's the same as minus alpha x minus beta x, just factorized with the negative out. So you can get this written down as we're going, please. And then I'm going to expand the brackets so that I have ax squared minus a alpha plus beta x plus a alpha beta. And we think that that is the same as this that we have here. And if you look at the x squared terms, well, the x squared terms are the same on the left-hand side and the right-hand side. So it's not particularly interesting to think about the x squared terms because they're both ax squared. But over here, I can see for the x term that plus b is the same as this. They must be the same as each other in order for them to be equal. So I'm going to write down that b equals minus a brackets alpha plus beta. In other words, alpha plus beta is equal to minus b over a. And then for the second part, if I compare the constant term, I get that c must be equal to a alpha beta. So c equals a alpha beta. In other words, alpha beta is equal to c over a. So this is the sum of the roots. The sum of the roots is equal to the negated b coefficient divided by the a coefficient. And this one we call the product of the roots. Okay? And we're going to start trying to spot some of these patterns as we go a bit further. You can see I've written it down in this purple box here. If alpha and beta are the roots of this equation, then the sum of the roots is minus b over a, and the product of the roots is c over a. And then we're going to try and see if this pattern generalizes. We're not going to go into the details of this table because we'll look at it more later on in this topic. But what we will see is that there are very similar relationships between our roots of higher order polynomials and their coefficients. So let's just explore this first table that we've got here. The first thing that we've got is this. We said the sum of the roots was minus b over a. And for a quadratic, the product of the roots is c over a. I can't do the sum of the products of triples because I haven't got three roots to do anything with here. But when you do this with a cubic, you also get that the roots, when you add them together, also sum to minus b over a. And when you do it with a quartic, with the four roots of a quartic, they also sum to minus b over a. The products of pairs, in other words, the product of two things together, well, we know for a quadratic, alpha beta is c over a. With a cubic, because there are three roots, there are three different pairs that you can potentially have. And when you add those together, you get c over a. And it's the same in a quartic. When you do all of the possible products of pairs that you get, it comes to c over a. We are going to prove this when we get to the cubic section of this exercise. For now, I'm just showing you that the reason we're interested in this is because it is true for all polynomials. And then you can see for the product of triples, for the three roots of a cubic, they go to minus d over a. And then when you do that for a quartic, when you do all of the triple things that you could potentially get, it also goes to minus d over a that we have. Andrew?
So, could you sort of figure out sort of what the roots of a cubic is just using those?
Yeah. You can. They're all connected to how you can solve the equations as well. So I've written down here that we can see that the sum of the roots, for example, has always has the same relationship with the coefficients. It's always minus b over a. Obviously, b is not always referring to x. It's the second part of the polynomial that we have there. So there's a pattern, and I've said what would be the product of the roots of a quartic, and it would be e over a. Because in a quartic, we haven't quite got that here, but if you multiplied all four of the roots together, I think it would be e over a, because look, it goes minus b over a plus c over a, minus d over a, so I think the next one would be an e over a. And then I've written it would be minus f over a for the product of the roots of a quintic, g over a for a sextic, and oscillating between positives and negatives. And these are known as Vieta's formulas, or Vieta's formulae. And we're going to see some of the patterns for quadratics and cubics. We're not going to prove these things for the quartics, but the relationships do hold true, and we can work these out to see that it works as well. We're going to go into this in a lot more detail later on. So back to the roots of the quadratics. For this quadratic that we've got here, I have x squared plus 2x plus 3. And we're going to find out what the sum of the roots are and what the product of the roots are. Well, clearly, a is 1, b is 2, and c is 3. And for part A of the question, the sum of the roots, alpha plus beta, is minus b over a. That's a standard fact that we can use, which is minus 2 over 1 or minus 2. So the sum of the roots is minus 2. And the product of the roots, ab, we know is c over a, which is just 3 over 1 or 3. I mean, that's pretty obvious. You could have told me that. Probably at GCSE, you could have looked at this and said, well, clearly the product of the roots is 3, and the sum of the roots is minus 2. So it's a nice, straightforward one. But do you notice how we found the sum of the roots and the product of the roots without having to solve the equation? That's really the theme of this chapter. We never really solve the equations. We actually just find the relationships between the coefficients and the roots without ever having to solve them. Everyone got that written down? Okay, so we're going to do a different one this time. The roots of the quadratic equation 2x squared minus 5x minus 4 equals 0 are alpha and beta. Without solving the equation, find the value of alpha plus beta, alpha beta, and then a couple of other things that we've got there as well. So very clearly, I would like to identify that a is 2, b is minus 5, and c is minus 4. So for part A of the question, alpha plus beta is minus b over a, which is just going to be 5 over 2. Part B of the question, the product of the roots is c over a, which is minus 4 over 2, which is minus 2. And then this is where things get a little bit more interesting. I want to find out what is the sum of the reciprocals of the roots without calculating what the roots actually are. What do you think I could do to these two fractions here? Yeah?
Wouldn't it just be the reciprocal of a?
No, because this is not equal to this. Because a half plus a third is not equal to a fifth. So I'm going to actually just add these fractions together and see if I can find something that happens. So how will I add these fractions together?
You need to make a common denominator.
And the common denominator is going to be
Alpha beta.
alpha beta. So that one needs to be multiplied by beta, so it will have a beta. That one needs to be multiplied by alpha, so it will have an alpha. So it's alpha plus beta over alpha beta. Yeah, so it's 5 over 2 over minus 2, which is? Minus 1.25. So if you think about it as this fraction within a fraction, if I multiply the top and bottom by 2, I would get minus 5 over 4. Because I've multiplied this by 2 and I've multiplied this by 2. No, it's fine.
Well, at least you went as a tickles me to think that you could add two fractions by adding a denominator.
I have to say, Andrew, that was a low point in your maths career.
And now it's going on the internet.
Okay, so we've got for the last one, alpha squared plus beta squared. Now, we need to do a bit of manipulation to try and find out what alpha squared plus beta squared is, because I can't solve the equation and find out what alpha and beta are. There's a few different things you could do. One of the things, if you wanted to, which I would advise against, is you could take this equation and this equation, which we know the numbers, and you could find out what alpha and beta are, but then that's technically solving the equation. The other thing that you could do is think to yourself, given that I know about the sums of the roots and the products of the roots, how could I generate something that has an alpha squared plus a beta squared? And it's probably to do with this one here. What could I do to this expression that would give me an alpha squared and a beta squared? Not perfectly, but it'll hint at it.
Multiply by alpha beta?
I could, if I multiplied this by alpha beta, I would get alpha squared beta plus alpha beta squared, and it's going to be a bit difficult to get the alpha squared plus beta squared there, so I don't think that's going to be the best way of doing that. What do you think, Andrew?
Because you know the formula of alpha plus beta is equal to minus b over a,
Yeah.
would you do b squared over a squared?
No, because alpha plus beta squared does not equal alpha squared plus beta squared, does it? So that's now the double whammy, Andrew.
Oh, it's a difference of two squares.
No, it's not a difference of two squares.
You do the difference of two squares.
So we are going to use this idea where it doesn't exactly equal that, but what we're going to do to explore this is we're going to actually work out what alpha plus beta squared is, and we're going to manipulate it to see what we get. So alpha plus beta squared is equal to alpha squared plus 2 alpha beta plus beta squared. So alpha plus beta squared minus 2 alpha beta is alpha squared plus beta squared, which is what we wanted. And we know alpha plus beta is 5 over 2. So I have 5 over 2 squared minus 2 times alpha beta, and alpha beta is minus 2. So you get alpha squared plus beta squared is equal to whatever this is. So that's going to be time for me to put up my calculator. So alpha squared plus beta squared is 41 over 4.
5 over 4 is 1.25, right?
Yep.
Well, I was there, and I thought I was wrong.
Oh, no, you were right. I was just doing it as a fraction. So we're going to be a bit sneaky now. We're actually going to solve the equation and check that all of these things we've done are right, okay?
What would they give this? Would they say in a question you can't solve the?
Yes, they would say you can't solve the equation.
If they see you solving it, would they say?
No, it's okay. You do this working out, but you can solve the equation to check it as well. Andrew?
So why don't you just say I didn't solve it and my calculator did for me?
No, that's silly. Come on. So we're going to do this quadratic. You've got 2 minus 5 minus 4 on the calculator. Now, when you actually solve this on the calculator, the roots are 5 plus root 57 over 4, and the other one is 5 minus root 57 over 4. So when you add these two things together, do you get 5 over 2? Well, come on, think. Yeah, you do.
They have the same denominator.
Yeah.
5 is 10.
So you get 10 over 4, which is 5 over 2. If you multiplied these two things together, I'm going to guarantee you do get minus 2. If you did the reciprocal of this one plus the reciprocal of this one, you would get minus 5 over 4. If you did this one squared plus this one squared, you would get 41 over 4. And you could check all of those things if you want to verify that that is the case. Okay? So we did all of those patterns without even having to use these. And it works with complex numbers as well. It won't just be for real numbers. It will also work for complex numbers too. So let's go on to another question. This time the roots of a quadratic equation are, they tell us what the roots are, and we're going to find the integer values for a, b, and c. So there's a few different ways you could go about this one. I'm just going to show you one of the ways. I'm sure you could come up with another way as well. But I'm going to say something that we know that alpha plus beta is equal to what? What was the sum of the roots? Minus b over a. So in other words, alpha plus beta, 5 over 4, so that's, sorry, minus 3 over 2 plus 5 over 4 is minus a quarter. So we have that minus a quarter equals minus b over a, or a quarter is b over a. We also know that alpha beta is c over a. And this times this, minus 3 over 2 multiplied by 5 over 4 is minus 15 over 8. Minus 15 over 8 equals c over a. And we're trying to find out what a, b, and c are. Is the quadratic that I've written at the top, it wants integer values for a, b, and c. Is that quadratic going to be a unique quadratic that has those solutions? Or are there going to be other quadratics that could still have those solutions? There could be other ones. What's the bit that would mean there could be other ones?
The A part.
The a part. You could multiply everything by 5. You could multiply everything by 10. As long as you've multiplied each part of it by the same value, the quadratic will still have the same roots. So because of the fact that the a part means that it could be different, the solutions could be different, I can just, you just pick a value. You can say let a equal 1. You could let it equal 1, you could let it equal 4, you could let it equal 8. But let's let a equal 1 because there are going to be lots and lots of different solutions. If a is equal to 1, don't worry about that, you're right. B and C will not be integers, but we will make them become integers in a second.
Would you then make a...
You'll multiply the whole thing through. So if A is 1, then B is... What's good, and C is... No, C is C over A. So C divided by 1, so you've just got C is minus 15 over 8. So that looks like our quadratic is going to be x squared plus a quarter x minus 15 over 8 equals 0. Good. We're going to now make everything become an integer because it wanted integer values by multiplying everything by 8. So we get 8x squared plus 2x minus 15 equals 0.
So,
Yes?
if you could, would you be able to prove sort of a quadratic is of the sort of same sort of values, or not value, but sort of the same, I don't know.
Roots, the same roots.
Yeah, roots.
Yeah, these quadratics have got the same roots.
Yeah, but could you just do it if you were able to sort of take a number and put outside a bracket a number,
Yes.
and then inside sort of like vectors?
Yes, if I could like factorize this by 8 and show it's the same as this, they'll have the same roots. Now, the alternative way that you could have done this question, that I think you probably could have done from GCSE, if this is a root, then we know one of the brackets is going to be x plus 3 over 2, and the other bracket will be x minus 5 over 4 to equal 0. You could expand these brackets, and you would get x squared plus a quarter x minus 15 over 8 equals 0, and then you would multiply by 8, and you would get the same thing. Now, this one is easier. However, this is not going to work so well for certain questions that we come across. I'm in this language for today's lesson and for the next few lessons, so I want us to try and think about these relationships that we have here, although of course there are alternative ways that you can do this. If it was in an assessment context, you think about which one is better, but for today we're exploring a new idea. So I'm not saying it's the best way, I'm just saying this is the idea that we're exploring. Okay, so I want you to have a go at doing this one. So we've got the roots of this quadratic equation. You've got what alpha and beta are. Determine the integer values for a, b, and c. I'm going to just do this one on the board. I'm going to do it the way that we were just doing it, and then let's see how that goes. Okay?
Do you want us to do it before you or?
I want you to do it before me. So you go. You start, and I'm going to start in 30 seconds to give you a head start. Do you get the same as me?
Yeah.
Okay, good. Okay. So the next one is just a little bit more interesting. The roots of the equation 6x squared plus 36x plus k equals 0 are reciprocals of each other. So I'm not going to write the roots this time as alpha and beta. I'm not going to do alpha and beta. What do you think I'll call the roots?
X and Y?
No?
Alpha and 1 over alpha.
I'm going to do alpha and 1 over alpha. No, because if I did alpha and 1 over beta, they're not linked.
I mean beta and
Oh, I'm sorry, yes, I could have done beta and 1 over beta, but I'm going to do alpha and 1 over alpha as my two roots that I've got here. So I know that the sum of the roots, alpha plus 1 over alpha, is equal to minus b over a, which is minus b over a. In other words, alpha plus 1 over alpha is equal to minus 6. I also know that alpha multiplied by 1 over alpha is equal to c over a, k over 6.
That isn't alpha times 1 over alpha just 1.
Perfect. So I've got these two facts here. This fact, I could find out what alpha is. This fact, I can just say that 1 equals k over 6, and so k equals 6. Look how neat that is. To find out the value of k, I knew that they were reciprocals of each other, so k was 6. I didn't even need to find out what alpha was in that first one that we've got there. Okay? If you wanted to, you could go about solving this equation and you could find out what alpha was. Just as a quick side note, which I'll do in a different colour, how would I solve this equation? What would I need to do first to solve it? I would multiply everything by alpha. I would have alpha squared plus 1 equals minus 6 alpha. Alpha squared minus 6 alpha plus 1. Thank you, plus 6 alpha plus 1 equals 0. But then basically it's the same as this quadratic, isn't it? It's the same quadratic,
So alpha equals
essentially.
6 as well.
Pardon?
Oh, yeah, of course.
So then you could solve that equation and you could find out what the roots are and you could substitute, but you don't need to. So just in case you came across an equation that looked like this. So overall, we did not need this, but we did need to use this product of the roots here.
So, if the roots are reciprocals of each other, will A always equal C?
If, yeah, A would be always equal to C if they are reciprocals of each other. Because we could say, yeah, you'd have alpha multiplied by 1 over alpha is C over A. Yeah, A and C are equal to each other if they're reciprocals. So you just start spotting these kind of weird patterns. They're not necessarily useful patterns. You're never in the middle of some kind of exercise. You're like, of course, like I should have remembered that the A and C are equal to each other because the roots are reciprocals. That's not the point of this. The point is just being like, oh yeah, cool, these things exist and they're there. So we're going to try a few questions from exercise 4A, but we're also going to do the cubics in today's lesson as well, because that's where it starts getting a bit more interesting.